Thank you guys tons for coming out. This is awesome to see even more people than last time. It was really badass. I'm a fan. My name is Zack Iszard. Some of you guys know me as the Chromatography Manager here at Confidence. Today I want to weave for you a tale of intrigue, betrayal, and romance. Actually, no, there's more confusion, unknowns, and a possible public safety concern. A glimpse into one small cluster of pixels in the growing image that is cannabis science. A new kind of chemical transformation is happening in a process that's fairly common. And through the observations of my astute coworkers, Beth, who's sitting over there, and Shannon, who's not present, the QA team here, they noticed some weird stuff in some potency results. And so I dug in. So imposter of what? I mean, this is all based on what? Oh, that's right. Hang on. So how did this problem begin? Well, really, we pull one of these. This is a spectrochromatograph on every single one of our samples. We have axis right here is the time axis, and then this is the wavelength axis. So we can see, like, that's our internal standard right there. That's some, like negative garbage. This is actually a specific distillate sample that I'll show you the regular chromatogram of later. That peak, I think, right there is THC, but it's not the biggest peak. We got this guy going on up here. That's something else. Don't really know exactly what it is. I think I have an idea. That's what this is all about. So we, just like all of the other labs in the state, like Steep Hill and Medicine Creek, both represented here today, we run Potency with HPLC and a UV vis detector. Really, that just means that we use the absorbance of ultraviolet light to measure quantities of different cannabinoids. At Confidence, we measure 8 different compounds. Other folks do other things. So this potency test has a wealth of information in it, truly a huge pile of information. There's many more peaks than those just matching our reference materials. We're looking for 8 compounds plus our internal standard. That's 9. The average guy has 15 or so peaks in there. So here's an example of a high CBDA CO2 oil, I believe. And you see a huge peak of CBDA. And some of you guys might be thinking, oh, that's flat topped. We're not measuring on those lines. We're measuring on the black one. We got some THC in there. I have no idea what that is. Looks like we got some neutral CBD, so a little bit of decarb. No CBN, pretty much. A little bit of THC and CBC. I counted this earlier. There are 16 peaks after the internal standard peak. And we're only looking for 8 of them. And 2, CBC, I guess, 1 of them doesn't even show up. So what are these other things? It's hard to tell, right? Most of the time, though, and this is why I really credit Beth and Shannon a lot with this discovery, this is what they look at all day. This is a Blue Dream flower. Looks like they harvested it a little bit earlier than they should have with the elevated CBGA level, but whatever. Again, we got this peak. It could be THCV. I don't know. Haven't looked into it. Here's another one. Pretty much looks the same. Here's another one. It pretty much looks the same. And you get the idea, right? Here's a BHO. That's also Blue Dream. Pulled from a different, all those flowers were pulled from different producers, run on different days. It's just that consistency of seeing just the same high THC strain over and over and over again. Some things look a little bit different. You can see in this BHO, for example, we have a little bit of decarb going on. Usually folks, heat the material to finish the purge. So we get a little bit of decarb. That said, heated extracts are totally different. You guys do know what I mean when I say decarb. It's decarboxylation of cannabinoid acids to their neutrals or actives, as it were. Sometimes this is done accidentally. So this is a CO2 oil, a classic CO2 oil, I guess I'd say, which is a raw product that is then winterized with ethanol, much like Amber's unknown vial that's sitting. Pass that thing around. So we see, we got quite a bit of decarb, but THCA is still pretty present. Same thing for CBGA. We got quite a bit of CBG neutral in there. But again, you see so many of these peaks, right? And we're pulling a spectrochromatograph on every single one of these. We have tens of thousands of those. And it's just sitting there, and there's tons of extra information in there, and no one knows what to do with it. research, right? This is an ethanol hash oil that's been fully decarbed explicitly for the purpose of adding to infused, beverages, edibles, what have you. Obviously, you want to decarb the whole damn thing in order to have as much potency as you can, because any THCA, like that tiny little bit that's left, that's not going to get you stoned. Here's another one. Again, fairly similar. You can also notice there's a little bit of CBN going on. Certainly more than we would see in a flower or most other kinds of concentrates. That's because of the heat exposure. But when there's another type though, that's a bit different. Distillate samples are the most varied and distinct, chromatographically speaking. This is the cleanest distillate sample that I've ever seen us actually test. This was about a year ago. In fact, I know the person who operated the machine to actually make this. I invited her. She didn't come. Oh well. She's missing out. That THC peak right there, quantified at right around 90%. That's what a lot of distillate manufacturers, I mean, James, would you guess that 90% is a reasonable target for someone's just starting to do distillation with short path? Right? I mean, that's in other applications, your first run through a short path distillation, and it's going to be 90 plus. My first time ever doing it in research lab, I got 98% purity on something. And that was with way more funky stuff, with way more impurities than what we'd normally be dealing with a refined cannabis product, right? But this is the exception to the rule. This is much more normal. So we have obviously a lot more stuff going on here. A little bit of a giveaway on our methodology. We use neutral pH, which is why we have our cannabinoid acids come out before our neutral cannabinoids. This might be a bit of a pain for this approach for dealing with distillates. It's great for everything else. But as you can see, we got some stuff going on. We have just enough resolution between CBG and CBD neutral, quite a bit of CBN, and then that's a new peak. And then what the heck is that? And that's also a peak, which I'm pretty sure is a cannabinoid based on recent MS data. This one I think was 82% THC. Well, there's 18% of other stuff somewhere, right? And generally you'd assume that if it evaporated and recondensed, it's probably almost all cannabinoids, right? Here's another one. You can see a little bit more of this stuff going on. And Beth and Shannon started to notice this happen on virtually every distillate sample that rolled through the doors. And we started getting frustrated customer calls, right? What is that? It happens on our method to almost perfectly coalesce with CBC. I talked with Dr. Aaron Stanek of Medicine Creek. He observed a similar phenomenon where there's this weird peak that shows up in distillates that elutes just a little bit before CBC should. Also, my friend Dylan Wilkes, who's a CSO at Orange Photonics, the maker of the Light Lab portable LC. That system is nowhere near as powerful as a proper analytical LC. Works for that purpose. It's refined for that purpose. But he, even with a lesser power chromatography, he was able to see the same thing. We have this weird stuff that's just like there, and it doesn't look like anything else that is supposed to be there. And sometimes it's really bad. This is the chromatogram of that of the sample I showed you the 3D printout of, and you can see that our stuff, our tail end mountain range or our garbage peaks or whatever you want to call them, are much larger than its delta 9 peak. This sample was 40% THC. What is the rest of the 60% is like, that looks like it's probably 40 or 50% just right there. And if we were to really, really drill into it, you can see there's a little bump right there, so that's a different compound. And then the main one, and then there's a little shoulder on the edge of it too. So there's 3 peaks right in that section. Not to mention that one, that little hump right there that's shouldered onto delta 9, that's delta 8. And then this guy over here, again, that one keeps showing up in distillates. It's at the very end. I still don't know what that is. So,
Zach,
yeah.
As you're talking about this, so are you going to talk about the different overlays you have there? Maybe you said it in the beginning that you have 4 different chromatograms.
Oh yeah, sure. Can I mention the wavelength numbers, Nick?
I mean, yeah, they're standard.
So we measure 4 different spectral lines with high resolution. So the spectrochromatogram isn't the pixel density, as it were. The resolution isn't strong enough for us to do great quantitation, but we do measure 4 spectral lines. The blue one, DAT A, is 220 nanometers. The Red one, DAD B, is 230 nanometers, DAD C is 250, and DAD D is 270. The reason that we see different, we see a lot of these peaks have like different amounts of those different spectra. I'll get to that. That has to do with the way they absorb ultraviolet light. And these frequencies are all fairly deep in the ultraviolet range. Cannabinoids don't really absorb visible light. They just don't. Thank you, Michael. So this is me standing behind the setup that was being filmed by Open Source Steel just yesterday. They were kind enough to let me step back and have a nice shiny picture. You can tell I got a haircut yesterday. So this is basically what a short path system would look like. I have a diagram, but because of this cool picture, well, screw it, I'll just go through the... So there are several different ways to isolate things, right? Chromatography, I was just talking about chromatography. That's a great way to isolate things, but it's really expensive to isolate a large amount of stuff because you have so much liquid that you have to get rid of after you've run something through a column. So instead, vacuum distillation is really popular. Regular distillation, like you're boiling water, right? That's a distillation. What vacuum is good for is lowering everybody's boiling points. So, if everyone probably has heard that you got to boil an egg longer if you're in Denver because the air pressure is lower, and the boiling point of water is actually reduced to, I think, like 93 Celsius or something like that. So the water's not as hot, you have to cook the egg longer. Ta-da. That same principle is how refrigeration works. The AC, for example, you just pull a really hard vacuum and so voila, stuff gets cold. Vacuum distillation is extremely popular for cannabis products because THC, all the cannabinoids are somewhat unstable. They can be degraded and they don't like to boil at room temperature. They'd much prefer to react and do something. CBN degradation, right? You guys are probably, most of y'all are familiar with the idea that THC can degrade to CBN, which is obviously not THC, doesn't really get you high the same way. Of the different strategies for vacuum distillation, short path is the cheapest and easiest to apply. Which is part of the reason that open source has been doing the work they've been doing. It's a really great place for folks that want to start with distillation to actually start it. That's mostly because it's just glassware, a heating mantle, a vacuum pump, and some stands. Special glassware, of course, but compared to industrial scale or pilot plant kind of stuff, it's much simpler and easier to figure out. Hypothetically, like I was saying earlier, it makes really pure THC, 90% plus seems reasonable, and then we get the phone call. Why is my distillate only 65% THC? Why is my distillate only 40% THC? What is the other stuff? Well, we kept seeing those weird peaks in there, right? The QA team finds that pattern. It's probable degradation. Let's just think about that for a minute. We have a product that has tons of this one thing, and then you put it through a process, and now you have less of it, and tons of something else you don't know what it is. That's probably degradation. Is that CBC? Let's just skip through that right quick. No, I'll talk about it. So this is how a short path works. That is real familiar for anyone watching this on Open Source Steel website. This is a still pot. This is where you put your stuff you're going to distill, a crude mixture. You got a thermometer to measure both the still head temperature and the temperature in the still pot, so stuff doesn't get too hot. You have this really short vapor pathway, which is why it's called short path. You have a condenser to condense things. This vacuum adapter at the very tail end is where you want to pull the vacuum from, not from over here, so you're not sucking all your vapor out that you want to recapture. And then you have a receiver flask right here. The vacuum trap, this is a really simplified version of it. The one that you saw in the picture I was in is a cold finger style. It's much more efficient for catching things. And then obviously a vacuum pump. So this is the structure of delta-9 THC. This is the structure of CBC, cannabichromene. This is the peak that is, it looks like, or we call it the CBC imposter. It looks like it's eluting in the same place. It has a very similar, if not identical, UV vis spectrum. Right, so I'll have to dig in some more. I only looked at a handful of samples to build this presentation, but Beth pointed out that sometimes the spectrum looks exactly the same as CBC. I don't think that, this degrades into this. Anyone who knows chemistry knows that that's almost certainly not...
Degradation
gonna happen. Like that's not like you gotta break that bond, and then you gotta shuffle that double bond around, then you gotta break that one, and then you gotta form a new bond between this carbon and I think that one, or that one.
You'd have to number the carbons to know.
Yeah, I mean it's a
Label them.
likelihood, right? What's likely? This is not likely. It's just not. Rearrange that many bonds? No, it must be something else. So if that's the, I use the word likely. I'm going to use the word likely a lot here. What's probable? We don't have enough hardware to know for sure what these things are. We don't have an NMR. We don't have Fourier transform infrared spectroscopy. Kind of wish for it, maybe if a university student that's interested is watching this on the web right now and wants to access our samples and isolate them and run them through an NMR, please give me a call as soon as you hear this. So distillates they're usually made from a crude extract solution. The open source guys start with a fairly concentrated raw ethanol solution. They evaporate the ethanol first, then the monoterpenes come, then the sesquiterpenes come, then the cannabinoids start to come. So, I mean, if we're talking about degradation, right? We're talking about chemical changes. That means we need to know what reactants are around for reactions to take place, right? Our reactants are anything in cannabis that dissolves in a solvent. None of those things are particularly aggressive. Myrcene and osamine are pretty reactive for terpenes. You can polymerize them, cyclize them. They like to do anything besides stay themselves. As the gummy mess on the osamine jar in that other room will indicate. But they're not that aggressive. They're truly not. I mean, they maybe help me, maybe something, but we're missing strong acids, strong bases, funky inorganic stuff, weird catalysts. We're missing all the things that hardcore chemists, hardcore synthetic chemists would normally use to commit fairly advanced chemical rearrangements, right? We're missing all of those things. The only thing we have in there is a little bit of oxygen, and it's just a little bit because it's a vacuum. It's dilute air. So our reactants it's a short list. So like I said before, the terpenes fractions leave first, and this is crucial. So yeah, maybe myrcene would react with THC, right? But it's already evaporated by the time the cannabinoids are exposed to a substantial amount of heat and are most likely to have chemistry happen. Generally speaking, the hotter you go, the more likely a chemical reaction is to occur. That's why food cooking is food cooking. You can't cook food at room temperature unless in ceviche, right? You use acid to cook it. So again, we're reagents to cause chemical changes. So our conditions are those of mild pyrolysis. That's the way that biochar is made. Well, aggressive pyrolysis is how biochar is made. It's basically just heating a stuff in a sealed container with no oxygen in it. Our heat is around 150, 200 Celsius when cannabinoids start to move. Is that about accurate, James? I remember that from y'all's presentations. Again, very dilute atmosphere, some O2, maybe a little bit of water vapor is absorbed in there. Water vapor is also a product of degradation to CBN, so again.
By the time you get to those conditions, there's not water left.
So, right, yeah, it's certainly very dilute, more dilute than the oxygen that's present. In fact, I actually, while I was making this presentation, I revised my hypothesis somewhat in light of, deeper thinking about exactly what conditions are there. The glassware itself shields most of the ultraviolet. Cutoff for Pyrex is, I think, 340 nanometers, which is just a little bit past the visible range, a little bit past deep blue. Ultraviolet is infamous for doing things like giving you skin cancer, and it does that by breaking bonds in your DNA. So certainly ultraviolet light could contribute, but our glassware, at least in the short path case, is blocking that. And in larger industrial cases, you'll be using glassware, or it'll be completely in the dark in a metal container of some sort. So light is not, it's just, okay, so hot glass surfaces. Maybe we have some reaction catalyst surfaces. Silica is a known, silica is a scientific name for glass, is a known catalyst for some reactions, so is aluminum oxide. So maybe we have some of that going on. It's hard to know for sure. Again, I don't have an NMR. I don't have all the big fancy toys other than an LCMS. I don't have all the big fancy toys to throw at this problem to try to understand it. You can just kind of infer things, right? So instead of just shooting in the dark forever, what does literature say about this? THC does degrade to CBN. This is a product that was made explicitly with that in mind. I think that peak of CBN was like 15 or 16% mass fraction. I can't remember what product type this is. I just like the chromatogram. You can also see that we don't get great resolution between delta 8 and delta 9 on our method. That first bump right there is delta 8. The second one is delta 9. One time I made a mistake of mixing the two in the same calibration vials. Oops, had to do that over again. That said, I feel, just from the chromatography by itself, I feel pretty strongly that whatever that stuff is, it's not delta 8, which is known to be psychoactive, by the way, delta 8 and delta 9. So THC degrades to CBN, cool. A long time ago, right after I first started working here, I was standing in front of a whiteboard. Come on. Standing in front of a whiteboard looking at structures that my predecessor had drawn up there. And he had this reaction diagram right here. So you have, that's delta 9 THC. And if you add oxygen and you rip off water with heat, you get CBN. But, I mean, we got 1, 2, 3 double bonds up here. It's the aromatic ring, but bear with me. 3 double bonds. We only got 1 up here. That means that we have 1, 2, 3, 4 extra hydrogens, which is why it's called tetrahydrocannabinol. This is just cannabinol. We have 4 hydrogens we got to pull off. That's not going to happen in one step. That's going to happen in multiple steps. So I tried to figure out what those steps would be. The halfway point between tetrahydro and no hydro is dihydrocannabinol. So if we pull off 1 water molecule, we get a DHC. And there are a couple of different structures that are likely to form. I figured that these two were the two most likely to form just because of rules in organic chemistry like conjugation and aromaticity. Zaitsev's rule, for example, which is why this double bond is particularly likely to form right there because it's fully substituted. We have 4 bonds coming off of the 2 carbons on the other sides. Then I found this paper called Phytocannabinoids, a Unified Critical Inventory. This is a fantastic meta-study. If any of this is in any way interesting to you so far, please go check it out. There's not a paywall on it. Phytocannabinoids, a Unified Critical Inventory. And I noticed that I found it searching for CBN degradation chemistry, and I noticed really quickly in this diagram, oh look, that's one of the guys I thought was going to happen. Oh, so was that one too. I didn't draw that one, but 2 for 3 is pretty good, right? And again, we're just kind of marching our way through from THC to CBN. Something I want to point out here. This little dot, the chemists will know that as a radical. That is a single electron. Normally electrons like to be in pairs. That was a single electron that got ripped off. When you have a radical that is adjacent to a double bond, they can flip back and forth. That's totally a thing. So, I mean, our conditions match mostly to understood pathways about more or less ambient degradation of THC to CBN. We have a whole lot less oxygen. That's the most critical factor. But as far as heat and time goes, I think generally to make CBN, you have to cook at 150 C in the oven for a couple hours. That's about how long a distillation run goes. So I would guess then our unknown product is less oxidized than CBN because we have less oxygen to do to chemistry, right? That's a decent guess. So I said delta 8 and delta 9, right? What does that actually mean? This is the current, I guess, modern accepted numbering diagram for THC. We're not going to worry about number 6, but 6A, 7, 8, 9, 10, and 10A are all somewhat important. And in fact, I don't think I even gave 6A a shout out. But we have 6 different THCs we can make. Here are 5 of them. This is delta 7, 8, 9, 10, and 10A. Might notice that the double bonds just kind of go in a circle around, right? Well, this is just because structures are a way of visualizing things and writing them down. I just arranged them here to show that. This is our principal guy, right? Delta 8 is also there. Well, the interesting thing that I read in that meta-study is that when researchers were first trying to figure out what made you high in weed back in the 50s and the 60s, they already knew ahead of time that this was one of the most likely THC structures to form. They thought that delta 9 was so unstable that it was almost certainly not going to be causing any psychoactivity because it just wouldn't be present in the plant. It would have reacted away there wouldn't be any of it left. They were wrong. That said, there are ways, as if, if I were to go back to that chromatogram where there was a CBN peak and a little bit of a delta 8 peak, it's possible to isomerize without too much difficulty, delta 9 to delta 8. How exactly it happens? I mean, I don't know how those folks prepared that sample. In fact, this is one of the reasons this group exists, is to try to share a little bit more information that, isn't absolutely trade secret critical, right? The conditions of analysis, the conditions of preparation, those things, I mean, they should be common knowledge. So I was going to read something off of this guy. So THC is less oxidized than CBN, but THC has a different UV spectrum than our unknown peak over there, right? I was talking about how it's similar to CBC. It's very likely that it has a similar chromophore to CBC. Okay, chromophore, back up. That's jargon, right? It means light bearer in Latin. I think it's Latin. Is it Greek? It's Latin. I'm just going to go with it. It's Latin. That is specifically the part of the molecule that interacts with visible light and is the reason that things are not transparent. Everything would be transparent if it weren't for interaction with visible light. Trippy, right? This is THCA, the A form. This is a highlighted version of its chromophore. It has this one big old chunky guy, and the key to a chromophore is it's delocalized shared electrons. It's like this big fluffy cloud of electrons that are just kind of swimming around on a huge part of the molecule, just chilling out, finding all kinds of nice nestled down, comfortable, stable configurations to be in. And as a result, it means that a larger chromophore can interact with lower frequency light more easily. Like chlorophyll, for example, I didn't add chlorophyll in here. Chlorophyll absorbs a little bit of red, like far red, and for a chromophore to absorb red light, that's really sticking it out there. It also absorbs a ton of blue, which is why we have a green plant. Right? It absorbs red and blue. We have green as either transmits or reflects, and ta-da. Well, using our own data, I can demonstrate this principle. So this is CBD and CBDA, again with the chromophores highlighted, and they're colored from blue to red based on how far into the red side of the spectrum they ought to be able to absorb. And sure enough, you see, with this big old fluffy guy, we got, I think, 12 delocalized electrons. That includes, lone pairs can come too, sometimes. We have this feature over here. This is nanometers. Visible, that's 400, is the deepest violet blue you can see. And the edge of the graph is 700, so that's the deepest red you can see. Infrared is past that. Right around 300, we have this maximum. There's nothing going on in CBD at 300. We got, this little hump right here. Most of it's just down low because we're kind of fragmented here, right? We don't have this big old group at donating. Every double bond, that's a delocalized pair that can donate, right? So we don't have that extra fluffiness. As a result, this chunk of the molecule just is a little harder to get along with. These guys, they don't really play a huge role because they're so tiny that they only absorb into the deep UV, pretty much from like 200 and back, which we can't measure with our instrumentation just because of the way that quartz is. Funny thing too, if you got the same chromophore in a different molecule, you get about the same spectrum, which is interesting and I think really cool. It's one of the reasons I like chemistry so much. This is THC, delta 9 in the middle. We got CBD over here, and we got CBG over here. If you're looking real careful at these somewhat pixelated drawings, you'll notice that THC does actually look a little, they look mostly the same, right? We got a big old chunk with a slope on it, and then a little bump right there. But THC's got this little feature. It's just a little bit down, whereas that is missing on CBD and CBG. That's because this oxygen's got a hydrogen on it, and this one doesn't. It's slightly different, but it's mostly the same, so it has mostly the same shape. Same thing is true for the acids. So here's THCA, here's CBDA, and here's CBGA, and again, we get basically the same shape, especially between CBDA and CBGA, because again, they have almost exactly the same chromophore. But because THC is bound up here, there's a slight difference. You get a little bit more of a dip right there, just a little bit more. Now, CBN right here on the left and CBC here on the right, they're unique among our 8 analytes in that there isn't another spectrum that they look like. CBN, of course, has this big old giant conjugated, I mean, that's a biphenyl ring with biphenyl meaning, you know, phenyl as benzene ring, whatever, bi meaning 2, and then we have the extra oxygens that are present in all the cannabinoids to just help donate. This is a very, very happy chromophore, and it can reach down pretty far, you know? It's reaching down and absorbing a ton, right where THCA and all that was absorbing just a little. And then CBC, it's a little bit different, right? It has this kind of weird shaped guy, and I colored it gold because it's not quite as happy as this one, but it's happier than the other ones that I colored like green and stuff. And notice that it also absorbs in this characteristic range. So, I was wondering, stupid Google thing. This is CBC, right? This is CBC spectrum. Remember, our CBC Imposter, that is the name of the main peak we think is a degradant, right? This is delta 10A THC. And if I'll go back to cycle through it again, notice how spectrum is, it's different, right? It's not exactly the same, but it's kind of similar. Almost. Well, maybe it's this guy instead, you know, with the bond going up instead of, you know, down to the left. That's slightly different. So maybe that would give us slightly different chromophore. This is delta 10 THC. I showed the structure on an earlier slide. I also mentioned that right there, when that radical forms, that double bond can trade places. So, if I may continue here, delta 10 THC has a very similar chromophore. The accepted reaction pathways leave the door open for this actually forming. So it's quite possible, if not likely, that other forms of THC, isomers of THC, are these degradants that we're seeing. General organic chemistry principles, I've been kind of talking about those kind of nebulously throughout. Just trust me, I'm right. Generally speaking, like I mentioned, Zaitsev's and Markovnikov's rules, not Markovnikov yet, they both suggest that these structures specifically are more likely to form given the conditions that we have. And then also the relative retention time. So if we're talking about our LC results, because it has to match that too, right? If we're going to identify an unknown, all the arrows have to point in the same direction or else we're wrong. The relative retention time would make sense too. It would come out a little bit before CBC based on how it's, and I'm happy to talk with the hardcore guys later about exactly why I think that's the case. So here's again that extremely degraded sample. It looks a little bit different now that I've presented the notion that things like that peak, that pile of 3 things, and that peak all might be different isomers of THC. Or who knows, maybe there's some DHC, the dihydrocannabinol, in there. To tell you the honest truth, reading through that meta-study, cannabinoids will do anything. But one thing I know for sure is that it's not likely to be hydrated or to have any substantial change to its polarity, its desire to dissolve in solvents, because that would have caused its retention time to disagree with our observation. So I've laid it out there. I think degradation in distillates are isomers of THC. What does that mean? For one, it's not delta 8 and it's not CBC. There are a couple of folks, none of them present, that are super pumped about telling a customer, oh yeah, that distillate you got, yeah, it's got a lot of delta 8 in it. It's like 60% delta 8 and 37% delta 9. That's a 97% distillate. The highest distillate we've ever tested was a total cannabinoid of 93. So 97 just on the reg, whenever our normal total canna is in a 80, 85 range for most distillates. I mean, it's straight up, it's wrong identification. I mean, you guys saw that the spectrum is different. It can't be CBC, and also the retention time is different. So just from our own LC results, we can see that those are both wrong. Okay, now moving past that, because this is just the nerdy stuff, right? What does this actually mean? Distillates can degrade. James, open source, have fielded tons of questions. In fact, Chris, if he's around, oh, there you are. Chris was talking about how fielding questions that they get from folks that are using their products and services, a lot of them overheating the material, not pulling a tight enough vacuum. So, I mean, the whole too much heat problem, you're trying to move the product around too fast, and then it just overheats, and you're basically cooking the cannabinoids. I mean, that's literally what's going on. You're cooking them. But it also means the distillates can be made well. If you pull an ultra deep vacuum, kind of like that one sample I showed you with the 90% THC with essentially no degradation, it is possible. So somebody's doing it. This is critical. So as a consumer, if you're buying a distillate product that's labeled at 94% THC, it's probably inaccurate. Yeah, they contain major impurities, and this isn't even the cut products. If Rob LaChance was here, he would be beating on that drum, and I'm right behind him. Right, cut distillates, or I'm sorry, cut vapes. That'll be a presentation for another time. So, are these impurities toxic? Probably not. I mean, most cannabinoids are like super benign, like less toxic than some spices. For crying out loud. Does the product lose potency if degraded? Maybe. Well, it could also gain potency. Who knows? Maybe Delta 10, Delta 10A are 3 times as potent as THC, and that's why distillates just get you ripped. Well, I have consumed some distillates. They don't get you ultra, super, super ridiculously ripped. It's, you know, it's about comparable, but it's different. Maybe some of those degradation products are desirable because it does have a different kind of effect. Maybe there are some medical effects that exist because of these degradants that you wouldn't get out of the plant. One thing that the meta-study pointed out is that other isomers besides Delta 8 and Delta 9 are usually very minor products and are likely just degradation products themselves in the plant while it's growing. So, I mean, maybe we figured out, you know, a synthetic entourage. Maybe, I don't know. I mean, this is the first that, as far as I am aware, if anybody has any corrections to this is the first I'm aware anyone's actually poking in to this problem to try to solve it, to try to figure out what's going on. So, how to show that this is really worth looking into? Gather more data. I really wished that I had enough time to gather some LCMS data, some dual detector data, to try to tweeze apart those things, because if you can't resolve it with chromatography, you probably can resolve it with mass spec. This is what I have done so far. I figured out how to run it for dual detector work. I approximated our normal method so that the peaks come out in the same order with about the same relative gap between them. I've also made some measurements. I've started to peel it apart, but I still have so much more to do. Many, many, many kinds of MS measurements. Eventually I'll get there. And eventually I'll come up with a way, basically a method, that will tell semi-quantitatively how much of all these different degradants are there, whether or not they're present, whether or not they exist in regular samples that are not exposed to heat and vacuum for prolonged periods, and so forth. And then put a lot of samples through that, of course, because, you know, how do you get data? In power, the number of samples. So, generally speaking, this is characterization. That's what a chemist calls determining the unknown, right? In a characterization study, oh, don't tell me you're going to do this crap again. All right, there we go. Publish all that juicy data, right? Once I keep saying I mean to say we at Competence here. Once we're sitting on all of that data, that's worth publishing. I mean, I'm hoping to get what I'm presenting now in a publishable form in the next couple of weeks. Even though it's just kind of like, hey, there's a thing, it might be this. It's not conclusive.
Paper that's out there in this area right now than anything, so.
Right, and the meta-study mentioned that there had been no major work published on THC degradation since the 80s. Well, now that we have this new industry, like Michael was pointing out, that safety and environmental consciousness, so that safety factor, right? What if these things are toxic? What if they're carcinogens? What if they're endocrine disruptors? Probably not. Probably, right? I keep using the word probably and likely. I mean, sometimes it's critical for a scientist to simply say, I don't know. I mean, I know what it isn't, right? I hope to have demonstrated a lot of the things that it isn't, but I don't know for sure what it is. I don't have the power to do such. So in a characterization study, we would say somebody's watching this and you want to do a characterization study. We would give you samples or source you the location to buy wholesale samples of material that have these degradation products in them. Then somehow, some way of isolation in a way that is not very economical but is that's extremely, extremely pure, and then throw that in our venerable NMR, the FTIR. Just to unpack these a little bit, NMR is essentially the same, kind of the same way that MRI works. You can see how the spins, how atoms basically interact with each other on a very local level within a molecule, and it can give you very, very fine, detailed information about the exact spatial arrangement of the atoms in a molecule, which is its structure, the spatial arrangement of atoms in a molecule. FTIR is great for telling you what kinds of atoms you're likely to find, so which functional groups. So a full characterization study has to include these two guys, generally speaking. I mean, there are some cases where you can't do one or the other and you have to do some others. But generally speaking, most modern characterization studies, especially on plant botanicals, use mass spec, NMR, and FTIR. So maybe that would fuel further work too. Maybe there's a way to refine the distillation process to target only one degradant. Or maybe there is medical benefit and there's a need to generate a large amount of this material to supply physicians and researchers with the things they need to actually run medical studies. So to sum up, cannabis science has been unexplored for decades. I think that Confidence Analytics and myself may be the first group to investigate this since the 80s, right? I mentioned that. Of course, that's a dead horse. Everybody knows cannabis science is underexplored. Eventually, that will no longer be true. Hopefully, in 5 years, if anyone's still watching this, this is definitely a dead horse and is no longer true. Progress is being made, but it's mostly by privately employed scientists like myself. A number of other folks, Amber presented some of her work with Avitas 2 meetings ago. A privately employed scientist. Universities just don't have access to grant money and the whole, it's federally illegal thing. So progress is being made, but it's not like real academic research from a certain perspective, right? Not research for its own sake. The reason I didn't have enough time to acquire more MS data is because, well, I got a job here and I do stuff. It's not as simple as just sitting in front of the MS all day and... Exactly, right? And where's our results? Where's our results? Whenever I'm like, oh, hang on, just give me another 4 weeks and I'll know what those degradants are. Then we'll be able to quantify them. That's not acceptable. We have deadlines to meet. That said, new science is definitely needed to keep up with product innovation. Short path distillation of cannabis products on a wide scale and with popularity is a very new phenomenon in only the last few years, really since full legalization has been a thing. Our regular method, which works great for flowers, BHO, CO2, bubble hash, keef, infused joints, hell, even edibles, topicals, beverages, tinctures, which I call infused solids and liquids, ISLs. It works great for all those things except for distillates because there's this weird stuff that's going on. So in order to really know what's there, we would need different chromatography, a different analytical method to pull apart what's there in that sample for real this time. So even routine, simple analyses, right, they're still in flux. None of this is settled yet. There isn't like a tried and true method. Everyone's still innovating. We're still settling, normalizing the industry. So cannabis is definitely proving to be unique in many ways, even to analytical chemists, right? You can't just apply old methods to the new thing and expect for it to work. Stay tuned for more bleeding edge topics at the confluence of cannabis and STEM. Real quick, I got some gratitude to give. First, CanSTEM, you guys are awesome. Us are awesome. For putting together a new group serving a very important and underserved part, well, maybe not so underserved anymore, part of this industry. Without you guys, I wouldn't have a platform for this, and it's just really fun to give a presentation that's like right dead center in the at least one aspect of this group. Obviously, Confidence Analytics. We remain a leading lab through powerful cooperation within and beyond. Part of the reason, in fact, one of the biggest reasons I'm a part of this group is because that cooperation beyond part is really critical. It's one thing to have a great team that you work with, and most people who like their jobs will be like, yeah, we got the best team ever. Yeah, everyone says that, just like everyone's got the best weed ever. But that beyond part, right? Being able to reach out to other folks and develop new things that you would not have been able to develop without cooperation. So we're hosting this time, maybe someone else will host next time. We're about to follow this up with a really brief lab tour if anyone wants to stick around before we go and grab beers. Then also Open Source Steel, thank you guys a ton for being out here to film and mic me up for this. And also for providing me a fair amount of insight. If I hadn't seen your class in person and watched some of the finer details that you wouldn't get just from reading about the stuff and thinking about it a priori, if I didn't have that exposure, I might not have had some of the insights that I had to come towards this conclusion that we have isomerization of THC in distillation. And also, of course, for recording. This is our first meeting that is having any kind of recording going on. That's awesome. Thank you, guys. And also all of you fancy attendees. I mean, without you, we wouldn't really have a group. So thanks tons for showing up and for supporting this group. I have one citation, just one. This is the phytocannabinoids, a unified critical inventory. I'm going to make sure this makes it to our repository.
It's really long, it's like 40 pages long. I have it.
It's a good one,
It
though.
is real good. It's so rich.
So much information, all the molecules, structures, everything.
All manner of stuff like, wait, the weed can make what? That? How? Because it's weed. It's amazing. All the remaining work in here is original and copyrighted by Confidence Analytics. A lot of the chromatograms, the spectrochромatogram, all that kind of stuff. That's all Confidence data. The structures and diagrams that I generated all myself, those are public domain. I'm probably going to figure out how to post them on, I don't know, like Google Images or something. A proper publication will have a whole lot of citations. I pulled a lot indirectly through the meta-study. I think I read maybe 3 or 4 specific papers around the idea of degradation and another 2 on THC reactivity in general.
The reference list on this paper is really good too.
It's hundreds of citations.
Hundreds of citations. So this is like a really good paper to have just for cannabis citation lists as well.
It's a really, really awesome paper. I'm really, I need to reach out to the authors and say thank you guys tons for doing such awesome science. Any questions?